Hello again, and welcome to today's webinar, How to Improve Safety and Productivity with Self-Driving Vehicles. My name is Lisa Shaw, and I'll be your moderator. I work on the marketing team at SICK, and I'm excited to be hosting today's session with speakers from SICK and Vecna Robotics. In this webinar, you'll learn how a Performance Level D safety system works and why you need one, how robots operate efficiently in a highly dynamic environment, what causes wear and tear on equipment, and so much more. Before we get started, I want to share that a recording of this webinar will be emailed to you following today's presentation. Also, feel free to ask questions at any time during the webinar by typing your questions into the Q&A section in your control panel. We'll take some time at the end of today's webinar to address as many questions as time allows. Also, during today's presentation, we'll be asking 2 poll questions, which you can also answer right near the Q&A box. And then lastly, after the webinar, please fill out our post-webinar survey and tell us how we did. Today's presenters are Jay Doyle, the Principal Embedded Systems Firmware Engineer at Vecna Robotics, Mike Baer, the Materials Handling Product Architect and Chief Electrical Engineer at Vecna Robotics, and Casey Santangelo is the East Coast Account Manager for SICK's Transport Logistics Division. Now I want to turn it over to them to introduce themselves and to begin today's webinar. So Jay, Mike, and Casey, please take it away.
Hi, everyone. My name is Jay Doyle. Thanks for the introduction. I have been with Vecna for about 5 years. I do embedded firmware and safety configuration for our robots, and I've been doing embedded stuff for about 20 years.
Hi, everyone. My name is Mike Baer. Thanks so much for joining us today. I'm the Chief Architect of Material Handling Products at Vecna Robotics. I've been designing AMRs and AMR Safety systems for about the past 8 years. Before that, I had a background in embedded hardware and software design, which basically means designing circuit boards and the software that runs on them.
My name is Casey Santangelo. I'm the East Coast Account Manager for SICK. I specialize in AGV and AGC applications. I've been working now with Vecna since I came on at SICK for about 2 years, but I also have a background in industrial automation for about a total of 8 years. But let's get started, Mike, and take it away.
All right, thanks, Casey. So a little bit about Vecna. So Vecna Robotics is the world leader in automated bulk handling. And so what does that mean? Well, if you look around the room that you're in, you see a lot of stuff. And almost everything that you see spends a significant portion of its supply chain time on pallets. And it's a real challenge to move all these pallets, sort of all that material efficiently. So when it comes down to it, what we really focus on is increasing both the capital and labor productivity for the logistics industry. And, a big part of that is how do you empower your human workers to accomplish more than ever before? So how do we do that? Well, over the past 2 decades, we've built an industry-leading software suite called Pivotal, which really does 2 things. And first, it turns any piece of industrial material handling equipment into a fully safe, autonomous mobile robot. And because of this flexibility, we've integrated with many of the largest OEM vehicles. And as a side effect of that, we've learned how to design safety systems that optimize the performance of all of these major manufacturers. And I just want to say that we're so thankful to SICK for partnering with us to help create the most advanced safety systems available in the self-driving industrial vehicle market today. And the second thing that Pivotal does is orchestrate all of the available resources within a facility. So it connects to your WMS, knows where all of your robots, humans, manually driven pieces of equipment are, knows what products need to go where and by what and when, and acts as sort of that grandmaster chess player. Make sure that all the resources are being used efficiently in real time. And, overall, the product has shown significant ROI. In a number of cases, we've seen that, without adding any additional resources, we've been able to over double the throughput of a facility by more effectively using the resources that they already had on site. And these are real deployed gains. These are not theoretical. And I want to take also just a moment to introduce Mass Robotics, which is an industry association that's co-founded by our Vecna Robotics CEO, Daniel Theobald. And it's focused on bringing innovators, customers, investors all together in effective ways to help move the industry as a whole forward. It focuses a lot on practical interoperability standards. It has a great co-working space in Boston. And the whole goal is, again, is just to help move the industry as a whole forward. And we think that this is so important because it's becoming increasingly clear that until the industry really widely adopts interoperability standards, we're sort of operating with one hand tied behind our back. And I'd say really putting an artificial cap on the amount of value that the industry can provide to its customers. And I guess by that, I'm not saying that the industry is not providing significant ROI to its customers today, because it is. But we just see a sort of step function event that if we can unlock interoperability between different hardware vendors and software, where anyone can write apps that run on somebody else's hardware, very much like how we saw the progression of the computer and cell phone industries. So just to sum it up, Mass Robotics, we believe is doing an incredibly important thing in moving this industry forward, and we would encourage you to check them all out. On the right here, you can see some of our public customers. We have a lot of non-public customers as well. These are many of the largest shippers, retailers, manufacturers, and 3PLs in the country.
And then I'm going to talk a little bit about SICK. I don't know how much everyone kind of understands or knows what SICK does. SICK's a sensor intelligence company founded back in 1946 by Dr. Irwin SICK. His first actual marketable invention was actually the light curtain for incident prevention. This technology is actually still used today. I'm sure a lot of you guys know what a light curtain is, but Irwin SICK was actually the leader and kind of innovator of that product. Today, still safety and environmental protection are in our roots, and we are still actually a family-owned company. Irwin SICK's wife actually still heads the management of the company in SICK AG in Germany. So now today, moving forward 70 years, SICK is one of the world's leading companies for sensors and sensor solutions. We have a huge portfolio with more than 50 subsidiaries now worldwide, with sales last year around 1.8 billion euros. We also have 10,000 employees. So we develop sensor solutions for companies of any size in any industry, whether you guys are big or small, kind of anywhere in the world, actually. And our products, we now have over 40,000 SKUs, and we spend a lot of time actually putting back money into our R&D side of things for development of new products. So I think each year around 10% to 12% of sales are returned back into the company to work on R&D, which kind of gives us products to work in Vecna Robotics solutions and stuff like that. We kind of work with leading edge companies to provide them products that they see in the future being beneficial. So we do spend a ton of time actually designing and reinventing new products. And from the help of companies like Vecna and stuff like that, we like to partner up with them and kind of get their input on certain products and kind of incorporate that into kind of their future needs. Talking to this a little more, I mean, SICK has close to 3,500 patents, and we're still growing. Some of the products we get into are detection sensors, positioning sensors, measurement solutions, a lot of identification products such as cameras, protection along with safety. We also have control and monitor solutions. So basically we have a whole encompassing breadth of product now that kind of gives a full solution versus just a simple end of the road sensor. We also get involved in systems and integration. So next, we would actually like to kind of hear from you guys. We're going to have a polling question, which I think our moderator is going to put a question in front of you guys, and we kind of want to hear back from you. So the question we have here is, are you using automation, AMRs, AGVs, or VGVs to optimize your workflows already? The response 1 would be yes, 2, no, but we're planning to in the next 6 to 12 months. No, but we're planning to in the next 12 to 18 months. 4, no, we have no plans to. And 5, I am an AMR designer. And I think we'll let you kind of take a second to answer that. I think the polling question will be on your right-hand side, but we do encourage you guys to answer. We kind of are looking for feedback from you guys as well. And then next, I'm gonna pass the ball back to Mike, and then we're gonna continue about dig into this PLD level of safety. So Mike, you want to take it back?
All right, thanks, Casey. All right, so why the shift to advanced safety systems? Well, first, there is and has always been a strong desire to reduce accidents due to manually driven industrial equipment. And in the past, training, careful hiring, and good supervision were some of our only tools really to solve this problem. But with the advent of AMRs, we have another tool in our tool belt. Statistically speaking, if an AMR is designed correctly, using a lot of the principles that we're going to go over today, it's just not going to hit anything. Here at Vecna Robotics, we have hundreds of thousands of driven miles on our system, and the only safety incidents that we have ever had are when manually driven equipment hits our AMRs. That as opposed to this year OSHA put out a statistic that there were 97,000 forklift injuries that occur annually, and of those 70% could have been avoided with better practices. So there's significant gains that can be made in safety by moving to AMRs. And of all the recent events that have been going on, it's really highlighted for me, and I guess the industry has been trending in this direction for a while, but the overnight demand spike seen in e-commerce due to COVID-19, coupled with the increased demand for a wider variety of SKUs has really highlighted the need to be able to adapt rapidly to change in ways that often aren't possible if you solve the same logistics problems with fixed infrastructure or traditional AGVs. Actually, a lot of what we're seeing in our customer base is the desire to be able to reallocate or retask their resources very, very quickly. One of the largest medical distributors in the US is a customer of ours who have had to make major shifts in the ways that they're doing things due to this sort of off-season peak that we're experiencing. So they're very interested in taking advantage of the flexibility of AMRs. Another example is one of our customers who deployed a lot of tuggers that pull trains of carts that carry pallets, or also what are called non-conveyable items. This surge in e-commerce has created a situation where customers are now buying things online that traditionally were were only bought in stores, things like tires, mattresses, kayaks. But anyways, they were using this particular facility in a certain way, but then their business needs change. And because they had invested in flexible automation, they were able to put all of those robots on a truck, ship them to a new facility, and have them running in that different facility in a very short time, which of course is very different than traditional automation, where you're building hard systems into a facility like conveyors, wires, or traditional automated storage and retrieval systems. Those can be hard because in the past you'd largely be able to plan and predict how the same facility would be used for 5 or 10 years. Today that's simply not the case for most of our customers. Another thing is we're starting now to see a shift that a lot of our sales leads are coming to us with their budgets in place, where in the past there was more of a sort of we'll wait and see where this whole AMR thing goes. But I think now there's a very clear realization that from these customers that we are vulnerable unless we take advantage of automation to make our operation more resilient. And, I find it especially telling, I think, that this is happening in a macroeconomic environment that we have today, where many of these companies are currently experiencing massive demand shock and hits to revenue. And the industry as an aggregate is cutting capital expenditures. Lastly, it's becoming increasingly clear as well that automation is not the right answer for everything. I think Elon Musk recently tweeted that over-automation at the Tesla factory was a mistake, and that, quote unquote, humans are underrated. Humans are simply much better at certain tasks than robots. And the gains to productivity of your operation can really be unlocked when you have humans and robots working side by side, where humans and robots are doing exactly what they're good at, respectively. And of course, in order for this to happen, there just simply cannot be any doubt in people's minds that robots are safe. So what is performance level D? So performance level D is a term that we're going to be using a lot in this presentation. Performance level D is defined in ISO 13849. And performance level D is just one performance level in a range of performance levels, going from levels A to E. Each performance level corresponds to a probability of dangerous failures per hour of an electronic control system, where a dangerous failure is defined as a failure that results in an unsafe state of the control system. So for instance, if a failure mode is readily detected and the control system is able to safely shut the system down, that particular failure mode would not be considered a dangerous failure and included in the calculation of those probabilities. And just going back to performance level D specifically, the category of D corresponds to probabilities of dangerous failures that are 10 to the -7 to 10 to the -6 dangerous failures per hour, which when you do out the math corresponds to one dangerous failure every 114 to 1,140 years of continuous operation, which is pretty incredible. One other point here is, which is incredibly important, is just because a control system meets performance level D requirements, it does not mean that it is safe. It just means that statistically speaking, the cause of an accident will not be due to an electrical failure or software bug within the performance level D safety system. There's an incredible amount of flexibility in the ways that a safety system can be designed. And with this flexibility comes the ability to design what are called safety functions to address individual hazards that are identified in the risk assessment process. But with this flexibility comes the ability to design safety functions that, although may meet the performance level D requirements, do not adequately mitigate the risk of the hazard.
Mike, you talk about software there for a second. I just want to make sure we all understand what we're talking about when we say software, and can you maybe elaborate what that means? Because our system has software and does high-level stuff, and we're talking about something like a little more specific, huh? In this type of.
Absolutely. So, I think a lot of the slides, specifically the one that we're on, we'll go into some of that. But the software that I'm talking about specifically is the one that is running, the software that's running on the performance level D safety system. So you can see on this slide, that there's two major parts to any AMR's safety system. So why don't I just start with this slide, and then Jay, if there's any remaining questions or things that you think I can clarify, we can do that.
Sure thing.
But so if you look at the 10,000-foot view of the entire safety architecture of an AMR, what you'll typically see is there's a multi-tiered approach to safety where the autonomy system and PLD safety system are running in parallel. These two systems are 100% separate, where each is not only running different software, but the software is running on totally separate hardware. And the software that I was just referring to in the previous slide is just the software that's on the PLD safety system. For those of you who are interested in learning about the standards that are governing this industry, ANSI B56.5 is sort of the standard that defines everything related to vehicle safety. So this would pertain to both systems described in the slide, both the autonomy and the PLD safety system. B56.5 defines everything from max vehicle speed in various situations to how close the vehicle can get to objects with any given sensing suite, what markings need to be present on the vehicle, as well as how to test all of these essential safety functions that we'll be describing. So I highly recommend familiarizing yourself with the standard if you are new to the space or interested in learning more. And we were discussing on the previous slide that just because a safety system is PLD, it doesn't necessarily mean that the vehicle is safe. This is where it's so important to utilize some of the third-party safety assessment services out there. There are many providers out there, but here at Vecna Robotics, we use SICK and have had nothing but great experiences working with their team. These services will go through the AMR's entire safety system. That's with both of the main systems that you see here. And they'll also take into account how the vehicle will actually be used in your operation. And they can be an incredibly valuable resource in maintaining the overall safety of that operation. I know we have both AMR designers and end users on this call. So I just want to be clear that these services are really useful whether you are the designer or the end user. So the main focus of this presentation is going to be on the PLD system, but just to make sure that everyone has a complete picture of how this system works as a whole, I wanted to just quickly go over the autonomy system's role in safety. So the autonomy system is really the brain of the AMR. It receives tasks, in our case from Pivotal, or in other cases from a WMS, and is responsible for breaking those tasks down into individual actions needed to accomplish that task. And after it breaks those tasks down into the individual actions, it's responsible for executing those actions and controlling the vehicle so it can complete that specific work item. And in general, it assumes that it is solely responsible for the safety of the system and that the PLD safety system does not even exist. And in this way, the PLD safety system is really just used as a backstop, where it's only ever forced to take action if there is a failure of the autonomy system's ability to keep the vehicle safe. The reason we see this type of architecture in AMRs is that the autonomy system is has much more information available to it, and therefore has the ability to make better decisions on what to do in any given circumstance. It also has more available actions that it can take compared to the PLD system. For instance, many times, if the autonomy system sees that there is an obstacle in the AMR's path, it can simply just plan a new path around the obstacle in real time without the need to bring the vehicle to a stop. In contrast, the only action that the PLD system would be able to take is to issue what's called a safe stop or an emergency stop to bring the vehicle's total kinetic energy to zero. If you look at the picture in the top left here, you see the total sensing suite of the autonomy system. So you can see it has a very high degree of situational awareness. It has 360-degree coverage. It's able to sense in all 3 dimensions, not just in a plane around the robot, which is what the PLD system is able to sense. So that's where it gets that situational awareness. And if you look at the top right, you can see the output of that sensing data and what the autonomy system's view of the world really looks like. So in this case, it can see some people that are in the world. And you can actually see the situation in the bottom right-hand part of this picture, where there is an AMR approaching these people. Those people are in its path, but because it's able to see them and because it has direct control over the vehicle's motor control systems, it's able to just plan around those people and not stop. Here we have one of our vehicles in production. This is a shift manager showing off his new toy. And you can see that, you know, as per what B5065 mandates, you know, there's some certain minimum distances. Once he got close to it, the vehicle came to a stop. In this case, it was controlled by the autonomy system, but if the autonomy system had failed to bring that vehicle to a stop, the PLD system would have kicked in. So that was the sort of view of the world from the autonomy system. What you see here is the view of the world from the PLD system on one of our integrations. The blue circles represent the field of view of the PLD sensors. And in this case, the sensing fields are not drawn to scale. They're actually about 9 meters. So they're much, much larger. But they are only able to view one slice of the world. And you know, one important thing to note is the positioning of these sensors determines whether the vehicle will be able to automatically resume after a safety stop. And what's important is that there's no gaps in sensing between the sensor field of view and the vehicle itself. In the diagram here, there are none. So a vehicle designed in this way would be able to automatically resume. But in some cases, you'll see a safety scanner that's mounted at an angle at the top of a pole or a mast on the vehicle, sort of looking down and sort of creating a curtain that touches the ground, let's say 5 or 6 feet in front of the vehicle. In that case, there's a gap in between the field of view of that sensor and the front of the vehicle. And that would be a system that's not able to automatically resume after a stop, because there's no way for the safety system to guarantee that nothing is directly in front of the vehicle where it can't sense. So with that, I'm going to hand it off to Jay to talk about how to safely and efficiently design the PLD system for operation in highly dynamic environments.
Thanks, Mike. I just want to take a second before I begin just to mention the poll results that you guys sent out. It looks like most of you didn't answer it, and those of you who did answer seem to either be designers like me or people who are already using it. So I guess we could take away from this that are preaching to the converted and to the silent. So I'm hoping that some of you out there who didn't submit an answer maybe are interested and maybe am using AMRs in the future, and I hope this helps you along in that process. So you go to the next slide, Mike. We'll talk about, first of all, why PLD, how did we get there? Why are we doing it in the first place? It's really not an easy thing to do. You definitely don't want to do this unless you need to. And the reason why we get to this point is because you start off the process by looking at your product and doing a risk assessment. And so you want to take a look at what the potential risks of your product has and what's the likelihood of them happening. And because our products generally are moving around heavy objects, they're moving around with some non-trivial speed, most likely that analysis comes to a conclusion that there's at least some amount of fatal risk. And that's the thing that sort of drives us to the conclusion, or drive anyone to the conclusion why you need to have it. So that's sort of, an important part of this whole discussion is doing that initial safety assessment and really getting a hold of what your risks are and really trying to think about what the probability of those are, and then sort of design your safety system around that type of analysis. Okay, go next slide. So I want to talk a little about so the nuances of the implementation. This is the stuff that I do for Vecna, is trying to configure our PLD system to make it work, and it needs to be safe, but it also needs to be efficient. So in some levels, it's easy to do an implementation that satisfies the PLD requirements. But what's harder is to really do an implementation that's not one where you lose a lot. So, a robot that's stopping all the time is safe, which is important, but it's also really inefficient. I mean, you're investing a lot of money in terms of buying these things with the hope of actually increasing, presumably, the efficiency of your workplace. So you really need to have a system that's going to be both safe but reasonably efficient. So what I generally try to focus in is trying to eliminate unnecessary stops, because that's the thing that really drives inefficiency, is robots that are stopping all the time and when they don't really need to. A robot that stopped is not moving products, and it's cutting through in your throughput, and it can be really annoying. So we're going to talk a lot about how to get a good implementation that's both safe and reasonably efficient. So I'm going to talk a lot about sort of eliminating stops as much as possible. So we're going to dig into a little bit of the details of that. And secondly, there's a second layer of this, which is talking about really trying to minimize some of the cost of the equipment by trying to minimize the wear and tear on the robot. We're going to get to that at some point too. There's a sort of second level benefit that we can try to optimize through some of our implementation. Okay, next. All right, so I'm going to dig down to some of the building blocks of a PLD type of safety implementation. And, all of these points all of these units are important in terms of the actual implementation. They all have to be rated at the same PLD level to be able to satisfy the requirements. Because if you have any weakness in this chain, then the whole thing falls down. You're only as safe as the weakest thing in that link. So all of these things are going to mention here. We're really looking for components that really give you that PLD or above level of safety rating. So our building blocks generally include encoders, right? Because encoders are important because we want to know, basically, we need to know how fast we're going. And that factors into where we're going to look and how far away we're going to look for those things. If you're going faster, obviously you need to be more conservative. You need to be looking for things a little farther out. If you're going slower, you can be hopefully a little more, you don't have to be as conservative. And so second level and with encoders is, I would argue you probably need to know something about your steering. This is a big part of what we found to be an ingredient for a really effective safety implementation, is if we can couple these two pieces of information, knowing how fast we're going and knowing where we're going, then we can really hopefully avoid stopping for things that are not really important to stop for. Things that we're going away from, obviously, don't really need to stop for those. So those are two big important parts of a good implementation. Next, obviously, is an important part is the scanners themselves. You need to have some sort of way to do obstacle detection. So this generally takes the form of a safety scanner, so a LiDAR-based scanner that's going to give you obstacle detection information to be able to see objects that are sort of along the lines that are enumerated in the B56 standard that Mike talked about. And that forms, the event that basically triggers your safety system to let us know that it has to stop and to start that sequence of events that would actually ensure that the truck comes to a complete stop. In addition to those two important parts, you're going to need to have something that sort of aggregates that information. So it's not just the sensors that you need. You need to some sort of logic that runs to sort of implement your whole strategy. Now, there's I've found that in our implementations we need some other information and there might be some other conditions in which we want to stop other than just the pure obstacle detection part. And then also there's some really important parts that have to do with how you monitor speed. That are really important in terms of getting a good efficient implementation. Those things, all these things are running on like a PLC type of safety controller, right? So that's the third part. Fourth part, we have all these different components. They all need to talk to each other. Now, as part of a system is a safe system is a system that has safe means of communication. So like for this SICK system, you're generally looking at like a safety FE Pro system. This is implements some safe means of communicating between these parts. And lastly, it's relay. So all of our implementations are sort of built on this principle that a safety system will be able to stop a truck by removing truck power. And these AMRs we build, they all have a parking brake basically engages when the truck power goes off. And you need to have a relay that basically is inline your truck power that you can pull when when things are not good. And this is a normally open relay. So if normally this is going to be keep the robot in a safe state by removing truck power. Those are our building blocks. Next slide. So I'm going to pass the mic over just to Casey just for a little bit so he can tell you a little bit about how SICK can provide solutions for all these different things. We have a little graphic here that shows you how these parts sort of get pulled together.
Yeah, thanks, Jay. So kind of, I guess, going a little further, which Jay will go even further into after this, but we're kind of going to look at like a simplified overview of the PLD safety system. This is like a common system, I guess we would see in like an AGV. So currently, like we would first, I think, looking at the encoder systems, we would have basically an encoder for tracking your velocity or speed, and then one tracking your steering. So SICK provides these two encoders that will go into actually the safety controller system through a module basically that pulls in that encoder data and then will translate that data and send that data to the LiDAR basically to understand what field set or area of protection needs to be set up at that time based on speed and direction. So the data going in from the encoders are going into the safety controller through the mock module, which is a SICK module that is added into our safety controller, which is the FlexiSoft safety controller. And that monitors the speed and direction and then pulls that through the controller. And then the controller sends that data over the FE Pro communication, which is an Ethernet-based safety communication to the PLD LiDAR. And then the LiDAR will adapt based on what it's seeing through the mock module. And all this is done through the architecture in the SICK software safety designer. And then obviously when something will break one of those fields, depending on the speed and direction those LiDARs are looking at, then ultimately the final straw would be the safety relay cuts out, and then we have a safe stop if someone breaks one of those fields. So I think Jay kind of goes deeper into kind of like how the microscan is programmed and how furthermore that we can kind of see how this PLD safety system works. So Jay, take her back.
Yep. Thanks. All right. Yeah, as Casey alluded to, I want to talk a little bit more about some of the details of some of these components, and specifically talk about the safety scanners, because that's really where a lot of the performance gains can be made, particularly how they are configured. Now, this slide just shows some of the basic building blocks we use here. So at least for the safety scanners we use for SICK, we use kind of a couple different concepts. So there's areas that we can basically define sort of fields. In this case, in the red zones here. These are the zones where if an object is detected in there, we need to stop. And that is the first part, the first event in that chain of events that will execute in the safety system to do a stop. And we also use another field as visualized in yellow that basically is an early warning system. It says like, I'm getting close to something. And this is an interesting thing. We're basically using this feature to actually push that information forward to the next level of our system outside the safety system as our early warning system. Like we do have a high level system that's doing lots of sensing, but there's another way we can sort of utilize the information that we already have in the safety system just to increase our safety coverage and our use of that data in our complete implementation. So for us, basically, like I said, we use this slow down zone to tell sort of our low-level system, hey, you should really start slowing down with the goal of avoiding stops. That's the big thing we're trying to do, is really want to avoid stops at all costs. And any type of information we have that we can act upon, that be useful in that information, we definitely want to use it. So typically, what we do is we look for crafting ways to make these field steps as optimal as possible. Now, in an ideal world, at any given point, there's a certain area that you care about, and it's based on where you're going and how fast you're going there. Now, if I'm going straight ahead, all I care about is things right ahead of me. Now, the safety system doesn't know about what the future plans are for the road. It only knows what the current state of the problem is. It knows how fast it's going, where it's going, and what direction it's heading. But in those two informations, we can change basically the areas of interest that we're looking for. And at any given point, there is a known area that is optimal. And every change of steering angle, any change of speed would change those zones. But in reality, you can't have infinite number of fields. So an efficient implementation has a lot to do with making good choices about how you do this. So 6 systems, and I believe probably others as well, basically break down speed and steering in discrete zones. So you take your speed, maybe you go from 0 to 8 miles per hour, and maybe you have 8 different zones based on 1 mile per hour increments. And maybe you take your steering, you break it down into 10 degrees per increments, and that sort of gives you sort of the whole set of combinations you need to be concerned about. And for each one of those combinations of speed and steering, there's a range of speed that you actually could be going, and there's a range of steering angles you could be going at. And you have to find an area that sort of encompasses all the possible ways your robot can go if in that particular state. But that allows you to sort of hopefully tune it in a way that's much more efficient than saying, I only care about things 5 meters from me, no matter what direction I'm going in. That's an example of an inefficient implementation, because you can find yourself stopping all the time. And a second part that's really important is that going down aisles is super important for our warehouse applications. Aisles are narrow, so this is really important in terms of navigating through narrow aisles. We want to be only focusing on the things we absolutely need to, because if we get too conservative and start looking to the side when we're going straight down to the center of an aisle, we won't be able to get through certain narrow aisles. So that's really important in terms of being able to make a product that is efficient and will even work at all in some of our applications. The other part I wanted to talk about in terms of these zones, the red zones, these things where we know we need to stop. There's a further optimization we can do is that we ideally want to not have to pull this parking brake unless we really have to, and we'll talk about that a little bit later on. So there is some implementation details that, and particularly with 6 implementation, that can be really helpful in this, in using the functionality that's included in their motion module, the mock module that Casey talked about. It's called the safe stop block. Basically, what it does is allows you the ability to monitor your deceleration. So if you know you have to stop, what we want to do is we want to tell the other parts of our system to stop the robot before we have to pull the parking brake. And so we can use that event and communicate it to the system and say, all right, you need to stopping right now, but I'm going to watch you. And I'm going to watch, and the safety system is going to watch you decelerate. And if you don't keep up, you're not doing your job, then I'm going to pull the parking brake. And that's a much better way of doing it, because it really gets to eliminating unnecessary wear and tear. And also there's some implementation details that tends to be a lot more efficient in terms of recovery time if you don't have to pull the parking brake. So we try to make as much, trying to use as much as possible to really eliminate stops at all. And when they do, eliminate the possibility that the safety system really has to do what it's designed to do in the worst case scenario, which is to pull the truck power. So I'm going to dig in a little bit and go to the next slide and look at some of the implementation details of some of these field sets. Next slide. Mike. Can you hear me?
I can hear you, Jay. You're good.
Good. All right. Good.
You're still there.
Wow. I would have not have liked to have done that all over again. All right. Here's some examples talking that sort of show you a little more detail about these field sets they're talking about and ways that we do an optimal implementation of them. So what we try to do is, like, for the combinations of speed and steering, look at try to find the right areas that we should be looking for, and in practice, what this comes out to is you always come up with a cone, because the cone is an artifact of the fact that you have a variety of different steering angles you could be in this state, and so that gives you sort of the spread, and the narrower you find the range of angles for any particular steering zone, the more narrow the cone will be. But it's different than, I think, a lot of invitations. They tend to be very straightforward, sort of blocks or just trapezoids and so forth. The more you can sort of implement a curved area, the more areas that you're removing that are potentials for false positive. And so another thing that happens when I have discussions with SICs, they ask me, well, how many field sets do you want? Jay, how many field sets do you want? And I always tell Casey or anyone who's listening, I will take as many as you can give me. And the reason behind that is that the more field sets I have, the more finely I can tune the system. I can break things up into smaller and smaller increments and get closer to that ideal area that I should be looking for, given what I know at any particular time. So this is just some examples of. You have some examples turn to right and turn to left and going straight forward, and then the one on the bottom right is actually backing up and turning. So each one of these is a slightly bit different. Maybe these don't show you the most exaggerated scenarios, but a lot of them have a convex curve that you can implement as a field set and the safety and the configuration of your safety scanner. And these curve sets do provide I think a pretty good benefit of really eliminating the false positives as much as possible. Next slide. Okay, yeah, I talked a lot about this, but two encoders, really important part. I would argue that just having your traction encoder is really not enough. You really need to have your steering encoder as well, just to be able to create field sets that give you a sense of really looking for the areas that you care about, and particularly for your going down aisles, for giving you narrow bands that where your safety system is looking for, and get around some pretty tight aisles for racking. Okay, next slide.
Thanks, Jay. And I just want to touch upon what you just said there about having it as narrow as possible field sets. One thing that we find is that the ROI of any particular facility that our customers have is typically directly proportional to the warehouse, to the density of that facility. So, the narrower you can make those field sets, it has a direct translation to the overall density of the facility that these vehicles can operate in, and the overall return on investment of that facility for the customer.
Yeah, great point. And particularly the straight ahead example is usually the most important. All right, let's go to the next slide. So it's going to run through a series of slides, which is a sort of low grade animation of a scenario of a robot going through a turn. Now, it uses some of the concepts we talked about earlier with some of the field sets and the warning zones versus the safe stop zones. So again, this orange or yellowy area is an area where the safety system is detecting an object that it knows it probably needs to slow down. That's going to be potentially problematic if nothing happens. and the red is an area where we have to stop. So we're coming around a corner here. We're kind of coming in maybe a little too fast, but we're heading straight ahead. And because we're heading straight ahead, we're looking directly in front of us, and we see the back wall. And this basically is going to generate an event that we push up to our low-level control system as early warning indication slows down. And as a result of slowing down, what's going to happen is we're going to choose a different set of field sets because we've changed speeds, and because of that that change of speed, it'll shrink. And so in this case, it shrunk a little bit, and now actually maybe a little bit. We may need to slow down just a little bit more because we're touching it. But this type of cascading event will keep on going, and so if we slow down a little bit further, that would back out a little bit more. And then we would actually be able to go, now we're able to kind of go into this turn without further speed reduction. So we're starting to turn the wheel, and as a result of turning the wheel, we choose yet a different set of fields that now is looking in the direction of our current travel, which is turning to the right and at a slower speed. And as we go around the corner, we're going to see all these change again as the steering wheel changes more aggressively to the right and slows down particularly a little bit as we're going through the corner. In every case, it's allowing us to get around there, and every selection of field sets is going to be such that we are still moving forward. And if anything, if we ever eventually touch the back wall like that, all right, we're going to kick it down just a little bit more, and then things will drop down a little bit more, allow us to keep on moving, albeit a little bit slower, until we finally come around the corner and get to the point where it straightens out again. And now we're back into a straightaway, and we can start accelerating again because we have the room to do that and pushing the field sets further out in front of us. Because hopefully that shows you a little bit of sense of how those pieces sort of work together to allow us to move efficiently through the area, not coming to a complete stop, which is definitely we don't want, but doing it in a safe manner. I think we talked about this a lot. Two encoders are important just to be able to eliminate the stops and to maximize, to be able to operate in maximally dense environments with aisles. Okay. All right. Next question. Here's your chance to, for all those who didn't participate in the first one, to go around. We have another minute for you to send in your answers. Where are the biggest areas of need for automation in your organization? General point-to-point transport, staging lane put away, line sides replenishment, workforce efficiency, and resource utilization, or anything else? With that, I think I'm going to hand it back to Mike.
Yeah, we'll let the group answer that in the background because we're running a little bit over. Last part of this presentation is reducing wear and tear through safe stops. Just in general, AMRs have a distinct advantage on wear and tear, just because, there are no collisions caused by the AMR in a correctly designed system. They have much softer accelerations and decelerations, so you're not wearing out that main drive system. But more specifically, and this is a feature that SICK pioneered. There's ways to implement the safety system so that you can reduce another main form of wear and tear. Before we go into that, I think we just want to take 1 second to talk about what is an emergency stop. So in a typical implementation, an emergency stop is when the performance level D system cuts vehicle power. Therefore, engaging the only mechanical brake in the system, which is a parking brake. And we work with many of the largest OEMs of these vehicles, and we work with their engineering teams. And I've asked the engineering teams of almost all of our partners, is this parking brake designed for shock loading? And they all say that it's not, and that repeated shock loads could cause catastrophic failure of that parking brake. And that's a big concern. It's a big concern, for the industry as a whole. Most safety system implementations will only use that parking brake, and if that does have a catastrophic failure, you've basically created a torpedo. I think that this is something that the industry needs to recognize and start to use some of the more advanced features that are available through fixed mock module, but I think some of the other safety system providers are catching on as well. So how does this work in a PLD way? You can implement something called a safe stop, which is, and Jay touched on this, but basically what happens is when the safety system does want the system to come to a complete stop, it will tell the vehicle's native control systems to bring the vehicle to a stop first. So that way you can use the motor controllers that are on the vehicle to slow down and come to a stop. And all the while, the safety system using that safety rated wheel velocity encoder is monitoring that stop. And only if there is a failure of the main control system to bring the vehicle to a stop will the safety system actually pull cut truck power and engage that parking brake. So in practice, we're really able to remove greater than 99% of the occurrences where we would have had to pull that parking brake. So with that, we'll conclude the presentation, and we will open up the floor for questions. And I believe we pass it off to Lisa at this point.
Yes, thank you, Mike, Jay, and Casey. We'll go ahead and take time for some questions. Any questions that we don't answer, I'll have our presenters reach out to you to answer them. But the first question is if the autonomous system is not designed as a safety function and the safety system is designed for PLD, how do you address collisions with objects that are not connected to the floor?
Yeah, the like overhanging objects, right?
Exactly, yes. Yep.
Do you want to start with that, Mike? I mean, obviously you can include safety scanners that are looking at different planes. That's one solution. But I think, I mean, does it? I don't know if you have more specific info about this.
I'd be glad to answer this. So, I think this all comes down to standards, and the reason B56.5 put the requirements in that you only need the horizontal plane for your PLD system is that really came down to a risk analysis of what are the situations where humans can get hurt. And that plane is defined to be at a height where whether a person is standing or laying down on the ground, they will be seen by that plane. And if you look at the overall risk of something not in that plane getting hit by an AMR, and then in consequence causing impact to human life, it's much lower, which is why the standard says that you don't need PLD for objects that are not in that plane. And in practice, what we find is that the autonomy systems, if they have the correct sensing suite, do a great job at making sure that we don't have those collisions. Like I was saying, at Vecna Robotics, we have hundreds of thousands of miles driven without a single collision to anything in that not in that plane or in that plane, and I know a lot of the other providers do as well. So I hope that answers the question.
Yeah, and Mike, if I add something real quick, like you said, I think it comes down to your risk assessment. I mean, obviously, if you're in a facility or something that has a ton of stuff that you could run into overhanging or something like that, you definitely would have to kind of understand that, and I think build a solution around that. And a lot of it doesn't even have to be strictly like a safety-based sensor. There's other ways. Using like multiple sensors or build in kind of almost like you said, like a separate type of thing to the software that can kind of detect these things and then do it well enough that through the risk assessment and stuff like that, you can kind of get away with that through the standards. Yeah.
That's a great point, Casey. And I just want to touch on one thing that you said, which is, making sure that, you have the right sensors to sense these things. One of the sort of fundamental tenets of the way that we've designed our system here at Vecna Robotics is that you should never rely on your understanding of where you are in the world, what's called your localization system for safety. So, I know a lot of the implementations out there will use what's called sort of no-go zones, or they rely on their map to, make sure that the robot's never able to go into an area that might have an overhang or something. But at Vecna Robotics, we feel strongly that, that localization system is not typically robust enough to meet the requirements for safety. So we will always go with the approach of making sure that we have direct sensing of anything that that we could possibly hit, meaning, we can sense in all directions around the vehicle.
Great. It looks like we're going over time, but I'll ask one more question. And again, any questions that we don't go over, I'll share with our presenters. But the final question is, does safety responsibility in an operation, including a public space, fall to the vendor or the actual user?
Can you repeat that again, Lisa? Sorry.
Sure, yeah. Does safety responsibility in an operation, including a public space, fall to the vendor or the actual user?
Yeah, so I can take this. I think when it comes down to it, the responsibility is certainly on both. The vendor is responsible for making sure that the vehicle itself is safe and conforms to all standards. But best practice is that when you do any new deployment into a new facility, you do a risk assessment of the actual operation of that vehicle in that facility. In that risk assessment, we'll look at things like, how close is the vehicle able to get to this pole, or are we creating any potential points where a human could get stuck in between a wall and the AMR, or maybe the carts that the AMR is tugging, and there's a lot of other little things that it will look at. The overall safety of the vehicle in the operation is the responsibility of the end user, but again, the overall safe operation of the AMR, meaning the AMR conforming to the safety standards, is the responsibility of the vendor.
Great, thank you. And thanks, Mike, Jane, Casey, and to our audience. That's all we have time for today. And thanks again for listening. Please visit SICK.com to stay in the know on our upcoming webinars. But have a great day, and thanks again to our presenters.
Yeah, thanks, Lisa. It was a great time. Thanks, Jay and Mike.
Thank you. Thanks, guys.
Thank you.